Right, let's begin the next talk. So it's my pleasure to introduce Cengiz Pehlevan from our own Department of Applied Math. Cengiz has many talents, but I know him especially as a leader in what's called the physics of learning, using physics ideas and methods to understand learning, which is the Nobel Prize Committee recently reminded us came before many of the other topics. So thank you. So please, Cengiz.
Thank you very much. And thank you for the invitation. So today's talk will be about solvable models. So I'll try to introduce a bunch of physics-style models to address certain questions in deep learning. And those questions relate to scaling and emergence. So this is a paragraph from GPT-4 technical report. And there's a section on so-called predictable scaling. What it says is the following. A large focus of the GPT-4 project was building a deep learning stack that scales predictably. The primary reason is that for very large training ones like GPT-4, it is not feasible to do extensive model-specific tuning. To address this, we developed infrastructure and optimization methods that have very predictable behavior across multiple scales. These improvements allowed us to reliably predict some aspects of the performance of GPT-4 from smaller models trained using 1,000 times to 10,000 times less compute. Right? So it's basically, you might have heard about scaling laws, the fact that neural networks, as you grow compute or data set size or model size, somehow their performance evolves predictably. It's not just an observation, it's also an engineering goal because it allows you to do all these savings. And then in that paper also they have plots like this. So this is a plot. What is plotting on the y-axis is some performance measure, bits per word. On the x-axis is compute. This amount of GPU power. You can translate this to dollars directly, right? So that's what it is. And all these little dots over here corresponds to smaller kinds of models that they are trained, and then fitted a curve, which is a power law, it turns out, to predict what might be happening at the maximum budget that they have, and basically make predictions about or how much compute should I throw to get those. Remarkable that basically, there is a very nicely behaving sort of power law kind of curve here, right? And then on the x-axis is some units of compute normalized to one GPT-4 unit, so we don't know what that is. But so this is one observation. We are living the age of scaling. And these power laws also often go hand in hand with the idea of emergence. What that means is the following idea, the idea that certain capabilities may not be available or expressed in a particular neural network for smaller sizes. But as you keep increasing sizes, these capabilities emerge. So, this particular paper, the brown paper here was very influential in this. I'm only showing a plot from this later paper from Ray et al. What they're showing is basically, again, on the X scale, these are all a bunch of different tasks. There's things like ability to do modular arithmetic and so on and so forth. And on the X-axis is some kind of model scale. And the point that they're trying to make is basically, the behavior, the capability seems to appear beyond some scale. Now, there is a lot of discussion. There's some controversy in the literature about whether these are jumps or they're more smooth transitions and so on and so forth. But at the end of the day, there seems to be also a capability, sort of emerging capabilities that's happening at large scale. So given these observations, multiple questions one can ask. So in the group here at Harvard, some topics we work on. For example, one idea is what are the limits of scaling? Meaning, if I were to take a neural network and just scale it up to infinite size, what does that look like? What does the limiting object look like? Can we understand its properties? If you believe the fact that larger is better, so these models are supposed to be giving us best performing versions of a certain architecture, so it would be good to understand what these guys are. Where do these scaling laws come from? Why do we get particular power laws? I'll say more about this. And emergence of these capabilities. At what scale do they emerge? What kind of training that you need to provide to these models for these capabilities to emerge? And so on and so forth. So for today's talk, I want to focus on these last two. basically I'll try to introduce some physics-style solvable models for both of them. But just to motivate those two questions, I'll say a little bit about this top one. And then just a few weeks ago, my student Blake Bordelon gave a talk where a lot of focus was on this one. I believe this is on the website, CMSA website, so you can also get update on that font there as well. Okay, so all right, so let's just review a bunch of things in this domain that I'll need for the rest of the talk. So first point is, what to scale? A particularly interesting and fruitful thing to scale has been width, meaning that's the number of neurons in a particular layer of, in this case, feed-forward neural network, MLP in this case. You could also think of scaling other things like depth and so on and so forth, number of outputs, number of inputs, and so on and so forth. And in general, people have worked out a bunch of these limits, including myself here, and they came up with sort of a big let's say, two classes of kinds of limits, right? So one is called the so-called the lazy or static or the kernel limit. It goes with different names here, and the idea here is basically this is sort of a limit where not very interesting in the sense that like the network does not adapt its internal representations to data, just basically processes data up until, as it's its initialization. Therefore, it's easier to analyze. Okay, it boils down to so-called a kernel method, but of course not realistic, because in well-performing neural networks, we know that internal representations adapt to data, and that's an important feature. So that kind of scaling limit doesn't really capture that fact. And there's another sort of a limit that people have called feature learning or rich or mean field limit. So these all refer to different things, but different routes to get into that particular classification. But for my talk, I'll mean the same thing. Okay, so in this infinite size limits, I'm not particularly talking about what goes to infinity yet. But roughly speaking, in this set of limits, network learns internal representations. And of course, it is harder to analyze, and then but more realistic. So we can't have best of both worlds. So it's two classes of limits out there. So basically, this is the infinite size limits. And then so we've done a lot of work in basically the second type, which is more realistic. Just to give you an idea of what might set, how we end up in limit A or limit B. So basically, it's mostly about parameterizations, how you initialize your neural network. So for example, in this particular case, we might choose our initial weights from a normal distribution, and then we have n units per layer, and then we might choose to normalize our initialization here by square root of n, so that we end up with a well-behaved, variance over there, and so on and so forth. The other thing we need to think about is our learning rate. If we don't scale our learning rate nicely, we might end up in a situation where the network doesn't train at all or trains too fast. So there's another parameter I'm going to introduce here, gamma 0. So this is going to be a parameter that only applies to the top layers sort of weights. And it turns out to have an important effect. The same thing appears over here as well. So this is my learning rate. Turns out, if I'm taking width to infinity, for example, if I keep this gamma 0 order 1, meaning it doesn't go with learning width, this network is going to be in so-called mean field rich feature learning regime, meaning even if this limit it's sort of internal representations about that data. Or, for example, if I also scale it with width, but with 1 over square root of n, okay, so basically, I think this is right. And basically, what's going to happen is basically this network is going to end up in the neural tangent kernel regime. It's going to not do anything. Basically, not learn any representations. I might have missed actually, I might have done this wrong. So I probably should have put a, so I think I'm missing a factor of square root of n here. All right, we'll get there.
So the different layers scale differently?
Just the last layer scales.
Just the last
layer scales.
Why the last one?
I mean, so one way to think about this is, so So what I should have said is basically, this is order 1 and this is square root of n, and I should have written a different way, but so if in the feature learning regime, this should go like W over n. What that means is basically on average, the output will be 0. And then what's going to happen is the error that you see, the network's output is 0. There will be compared to some error term. That will be a finite number. Just I'm giving you some bunch of intuition here. And what that's going to do is basically push gradients all the way, big gradients all the way deep into the neural network. In the other case, basically, the outputs will have a finite scale. So that's one way to think about this. All right, so this will not be too important, but the fact that there are 2 different regions is important. And then a bunch of people, including myself, have worked out basically these mean field limits. So you can describe these dynamics in this limit using a bunch of stochastic differential equations, or actually like integral equations in this case, but fine. They have differential forms as well. But so there's a bunch of papers that work these things with MLPs, ResNets, and transformers. There are other papers from other authors. So there are 2-layer versions here. These are deep versions. And then there's also the tensor programs that work with Yang and Hu, all studying the same kind of limit. So this is all I will need from this section, that there exists these limits. And you can even write down these dynamics. They're very complicated. I can give a whole talk about this, but I will not. Okay, what I will focus on is basically these guys. So what is the implications of the existence of these limits for setting scaling laws and power laws? And that comes from the observation of following observation. Okay. So this is a paper that's studying basically fluctuations 1 over n, or 1 over whatever it is that you're scaling, finite size fluctuations, again, around these dynamical mean field theory limits. And on the x-axis in this particular case is width. And then on the y-axis, we're plotting basically a bunch of observables. These are the things that the dynamical mean field theory studies. For example, the tangent kernel, the network's predictor, and so on and so forth. And these are the objects that are supposed to concentrate as width goes to infinity. And we're looking at basically those objects and their deviation from the infinite width limit. These averages refer to averages over initialization. And the finding here is basically what you're supposed to see is that these deviations should fall like 1 over basically n being the thing that you're scaling. So it's a very expected behavior. Something's concentrating and the fluctuations around it basically should have this kind of a behavior. Okay. Now the question is, this does make a prediction about the scaling laws that you should be seeing in these real-size neural networks. If they're around these infinite size limits, in the vicinity of these limits, basically you should be seeing such kind of behavior. And let's test this idea. So this is a bunch of simulations. These are SGD dynamics or vision transformers trained on C5M. H is the number of attention heads in this neural network. So what's happening here is basically this is an online setting. Y-axis is test loss. X-axis is the number of training steps that you're having. And these are all basically different size neural networks where we're scaling, in this case, number of heads. Okay. And that goes into all these parameterizations and so on and so forth, which I'm not going to go into. But several points to be made about this. One, as you're scaling up, it sounds like you seem to be converging to a limit, so that's nice. To the extent that basically behavior is very consistent, you see like data is presented in the same order here. So you see even these little kinks in the dynamics being repeated across different bits. So that's a pretty good sign that you're closing approaching your consistent behavior. So let's test this idea that whether basically the convergence here is like 1 over number of heads. And we're going to do this in multiple places. We're going to do this across different time steps, across training, so early and later and later and later. So that's what's been plotted here. Okay? So I'm going to look at the difference between this value and some large f of f, h large as a proxy for h infinite, and how that falls. So for early training, steps 2500, basically you're seeing that the fall is like 1 over h. But as you're getting to later and later times, basically you're deviating from this 1 over h prediction. So what this plot is telling me that basically early in training, I'm within basically this mean field theory kind of dynamics. Hopefully that's still an if, there's no proof, but basically it's consistent with that behavior. But later on, whatever is happening here, I'm not described by this traditional 1/n deviation, 1/h deviation from the event. And so what's happening is the question, that's what we need to understand. Any questions? So that's the basic observation that I want to talk about in the next, whatever, 25 minutes or something. So this finding is actually happens in a lot of things. So this is ImageNet. What is this? This is some ResNet trained on ImageNet. This is, again, some transformer trained on Wikitext. There are different things being scaled and so on and so forth. And again, basically, these are like different kind of training curves across different scales. And if you look at later in training, in both of these cases, you will find that basically like the loss as a function of whatever is being scaled is not following like a power law that's 1/n, and in this case was width, but it was a different power law, in this case 0.42 or 0.63. So why is that number not 1? So that's what we're after. I should point that for other data sets like CFAR10, simple data sets, at sizes of neural networks that fit into a single A100 GPU, actually, if you train it to the level of state-of-the-art sort of performance, you will get 1/n all the way to the end. So those networks, at least for those data sets, might be within the finite width sort of corrections to a mean field limit, but certainly these data sets, for these networks of these sizes, are not. Okay, good. So that's not true. And also, I mean, if you can look at the scaling exponents from these two big studies that people might be familiar with, the Kaplan study and the Chinchilla scaling law from Hoffman study. So these were large-scale, basically, scaling law studies where in both cases the authors simulate a bunch of networks and fitted the loss with these parametric forms. They are different forms, but I mean, these are what they tried. So in their case, I mean, N here refers to network size. So it's not actually width, it's a whole number of parameters, which includes width, depth, and so forth. And T is the number of training steps. And NC and TC are some constants in this case. And then in Hoffman's case, it's again, this is some baseline. And scaling exponents, as you look, they're not one, they're just some other number. Okay, that's the point. Okay, good. Yeah, all right, so exponents are non-trivial. By non-trivial, I mean not one. All right, so how can we understand this? Is there a model, simple model that we can solve that captures this behavior and also gives us insight about where that numbers might be coming from? So I'll introduce this model, a dynamical model of neural scaling laws. So this is basically related to many other works as you're seeing over here. Okay, in particular, I mean, I'm highlighting 3 models that are very similar to what I'm going to describe. And then there's an idea here of a dynamical. What I mean by this is previous models were looking at this at the end of training. So here I'll also consider number of training steps that you get, but that won't be the main. So that will be one extra contribution over previous case. And the way I will promote this is the following. So main ideas of the model. Okay, so I'm going to look at this very simple model, simplest model I can think of, where I can vary the number of parameters, data set size, and some training time. Okay, so the way I'm going to do this is sort of a gradient flow or mini-batch sort of a gradient descent kind of thing. And then for the first few minutes, for analytical tractability, I'll consider the lazy limit of neural network training. I'll later talk about generalization to feature learning. And then I'll also make the observation that in the lazy limit, neural networks are kernel machines, and the infinite sort of width limit, the particular kernel is a neural tangent kernel. And then, so here's the main modeling idea. Kernels of finite width networks are noisy versions of the infinite width models. Okay, so every model has a tangent kernel. Infinite width models have some deterministic kernel out there. The finite width ones have some noisy versions of this. The question is, how can I model this noise? So if I can get a reasonable model, then this might give me some sort of idea about where these interesting power laws might be coming from. So I said this whole problem was a so-called teacher-student setup from statistical physics. Okay, so here's the idea. So I'll do a so-called Mercer decomposition of the infinite with NTK. So the idea is basically, sorry, this is not working. Okay, so this is the infinite with kernel NTK. It takes 2 data points as input. We can diagonalize this in this basis of so-called features or eigenfunctions. The idea is that these eigenfunctions are orthogonal under the data distribution X, and then also, there's a corresponding eigenvalue here. So this is just true. And then here's what we're going to do. We know that these eigenfunctions are a complete basis in the space of square integrated functions. So suppose now, all right. Okay, so this is the infinite guy. Now suppose I also have a finite width model. Okay, so by a finite width model, I will mean, okay, I'll initialize a neural network, collect, maybe find its own tangent kernel, do its own diagonalization, and assume a linear model on top of this. This is in the lazy regime. That's how a neural network behaves like. The point I'm trying to make is these eigenfunctions are not the same thing as these eigenfunctions. These are coming from the infinite with kernel. This is just a finite with kernel's eigenfunctions. Right? Cool. All right. But the point is that, these guys are a complete basis, so I can expand each of these guys in that basis with some coefficients. So that's just a fact also. So what do I know about these coefficients? Not much. One thing I know is basically as size goes to infinity, this should be basically an identity matrix. And then measuring these and coming up with theory with these is really hard. So what I'll do is basically assume the simplest random matrix ensemble that has this property. So I'll assume that basically this guy is coming from just a Gaussian elements of AIG are driven from some Gaussian, and see the consequences of this. So I'm going to assume that basically the finite with kernel is a random projection of the infinite kernel.
But wouldn't you expect that the first eigenfunctions are better approximated than the higher ones?
This is true. This is certainly true. I could certainly introduce more structure here.
Yes.
Yeah, exactly. This is the simplest thing we went with. I'll compare just the real things, and I'll tell you where it fails and where it succeeds, and we can talk about this. Good. And then also there's going to be a teacher. The teacher is basically what the examples are generated from, right? So these are guys that are expanded in the top guy's basis, and it has its own weights in that thing. Okay. So this is the setting. And then I have to come up with some kind of statistical model for data. I'm going to sample x's from some distribution Q of x, assign labels by this mapping over here, add some noise, and so on and so forth. Okay, good. And then basically, given a data set of size p, do just gradient flow and see what happens. Okay, good. So I'll just consider gradient flow and MSE loss, mean squared error loss. So here is the thing that we need to track. So this is the difference between the teacher weight and the student weight, which is a combination of those guys. Okay, and then so basically, if we do a MSE loss, and then basically there's a gradient flow equation that's basically described in terms of this P0 vector given by here. And when you look at this equation, now you see what's happening. That there are two sorts of randomness here. One is coming from these two random matrices. This is my random projection. And these are my data matrices. So let's just come back to one slide. So basically, I take a data, pass it through this infinite with features, and then call that into a matrix psi mu k. And that's the random data matrix over here. Okay? So I have to find the limit where I can sort of like take some things to infinity and basically average over these using some random matrix theory kind of tricks. So that's what we do. Right, so what we're going to do is basically, so we do this using, again, a method from physics, a path integral, Martens-Giraud's formalism, and Gaussian equivalence. What that means is basically we're going to assume that the distribution of psi or the effect of the distribution of data when passed through psi features can be captured by its first two moments. Okay, so in certain settings, people have studied this to be true. Here we assume that is true. And then we're going to study the limit where basically number of samples for this kind of thing, and then number of basically n being the number of n is the limit of the, sorry, just make sure I've good. Then is the n is the size of the student network going large. So we have to average over two types of disorders: initialization, A, and data. So you can do this. I'm not going to go into the details of this. So this is shown in gradient flow picture. You can also do gradient descent picture. These equations become discrete and so on and so forth. I'll just tell you what comes out. Okay, so there is going to be a full asymptotic learning dynamics that we can characterize in terms of a bunch of sort of summary statistics. So if you look into those equations and basically try to extract from that some lessons, so that's what the lesson is going to be in the next slide. Okay, so here's what we're going to assume to be able to go to the power law picture. So we're going to assume two things. These are called source and capacity constraints in earlier literature from information theory. So one is the idea that these eigen values should decay like a power law, okay, that power exponent being B. And the second thing is that basically these teacher weights also going like a power law, normalized with lambda k. So these are assumptions that I'm going to put in. Later on, I'm going to show you some in real data, these actually hold to a large extent. So I'm going to show that in a second.
So any problems with multiple eigenvalues?
I mean, degeneracy. So
Yeah.
there is no, yeah, we will not assume degeneracy. That, I mean, so if that doesn't really happen.
Okay.
Yeah. Well, I mean, you can, so I should get careful. In some of these papers, people have studied cases where there's degeneracy and that has big effect on what I'm going to say.
Yes.
Okay, but for what I'm going to say now, it won't matter. Okay, cool.
Can you comment on the name? Why is it called source?
Actually, I'm not exactly sure what's coming from. The capacity, I think, refers to the ability of the kernel to be able to resolve.
Yeah, the capacity of that.
Yeah, the source, I don't know. I mean, I learned this from Hugo's paper, so maybe Hugo is here. He can tell me exactly why. He doesn't know either. Okay, good. Okay, all right. So, but here's summary of, so we have an exact expression for the loss as a function of TP and N. So here are several limits of this, okay? So I'm going to consider three different regimes. I'll call them time bottleneck, data bottleneck, and model bottleneck. Time bottleneck means I've given the model as many data as possible and as large a model size as possible, but I've taken a few training steps. So that's bottlenecking. Data bottleneck will be give as many training steps as possible as you want, take a model size to infinity, but you're operating with few data. Model bottleneck will be the corresponding term where TNP goes to infinity, but N is like small. So there will be, so what you will observe is basically this object over here will be basically following with a power law in the bottlenecking parameter, okay, but not in other things that go to infinity. Okay, so right, so and the exponents here are basically functions of these things. I'll try to give you an intuition about where these exponents come from in 2 slides. But let's see what happens to this model. So here are some simulations. This is setting off the model itself. So we generate some data from some distribution that we control, and then so on and so forth. So this is number of training steps, 1,000 test loss points, test loss dynamics. These are different model sizes. So what you're seeing is basically this. This blue line is the prediction of basically being a time bottleneck thing. So basically when the number of data points and N goes to infinity, you should be following this line. But as N is less than infinity, you keep deviating from that and so on and so forth. So if I look at basically what's happening early here, right, as a function of N, early time model convergence, I do get a 1/N convergence. But late time, right, I'm now bottlenecked by the network width now, okay? And basically the scaling loss basically follows the bottleneck scaling loss coming from here. Okay. So the model exhibits this transition from 1 over n to 1 over n to the minus a minus 1. I didn't give you the intuition of why this is coming from. I'll get there, but just to tell you again. The same thing happens for data set size as well. Now I'm fixing networks width and varying p being the how many examples I give. Right? So as p increases, I get approach to this basically infinite bottleneck. Time constant, early in training, I converge to the blue line with p minus 1 power law, but later on I get to transition to my bottleneck. So this basically captures that particular behavior. So why is this coming from? Why is there an intuition that I can give you? Okay. So after working on this for years, this is the best intuition I have. It actually works. This is amazing that it works. Right, so here's the idea. So because we're dealing with a mean square loss, right, I can diagonalize this mean square loss in different modes. And basically, in each of these modes, what you can do is the following. Right? There's going to be some modes which are fully learned. Okay, error there is 0. And there will be some modes which are not learned at all. Okay, and the error there will be whatever is the power in that mode is. That is exactly the square of that mode. Okay. So basically, there will be a sort of threshold here, above which I haven't learned anything, and below which I learned everything. So if I sum this tail, I end up with basically power here. So what is that K star? Okay. So for data bottleneck, K star is also P, right? Because the idea is if I give you P points, I can resolve at most P dimensions of the kernel of the data. So that's what that is. Same thing with model bottleneck. If I give you a model of size n, the kernel has a rank n constraint on it, so it can resolve n dimensions of data. It's again the same number over here. And then time bottleneck is a bit more, there needs to be another thing, because basically there's a time constant. The number of steps that you need to train also depends on the time constant, which relates to the inverse of the eigenvalue over here. So if you convert that currency over basically, that comes to a factor of 1 over p, and that's what goes in here, and that's the model. All right, so basically, long story short, okay, so I tried to argue that these deviations from 1 over np or whatever it is that you're scaling behavior, at least in this particular model, it's coming from some kind of resolution limit, meaning that the model either doesn't have enough rank, that's coming from the kernel rank, or enough data or enough number of training steps to resolve basically everything you solve, and that's basically what's limiting it. Okay, so let's apply these ideas to, let's be brave, okay? And apply this to some resonant train on C55. So let's see what happens. So here's what we're going to do. We're going to take this data set and take our initial tangent kernel, diagonalize it, and plot its eigenspectrum. And that's going to be given by this. Okay, so this is basically values, right? Exactly. So across different, n here refers to the convolutional channels that turns out to be the right metric for width over here. So, you do get some power law that goes maybe k to the minus 2 or something. Okay, we're not going to be too careful about filling these things. The second one is, okay, this is related to the particular combination and how that falls. Now, this is a very noisy thing. So instead, I'm plotting what I call a cumulative sum. So basically, I'm summing up to a ck to a particular point. Anyway, so the point is, this is supposed to have the same power law as the other guy. This doesn't really look like a power law, but I'm just going to assume the best sort of powerish while looking constant here, 0.15 and 0.2, and plug into my predictions and see what I get. So these are simulations. The x-axis here is compute. So I did one more trick. Instead of looking at the function of number of data set size and steps and so on and so forth, I combine them all into one unit called compute. So there's no cheating here. It's just another way to plot. And then, so what I see is basically that this particular exponent that I get from the theory matches what happens in so-called lazy regime. That was my assumption from the beginning. But for the feature learning regime, I get a different exponent, so I don't catch that. Okay, so I declare this part success. I declare this part failure. All right, so can I do something better? All right, so in this latest NeurIPS cycle, so we have in this latest whatever conference it is cycle, we have the submission where now instead of just choosing this randomly and training this, now we train both layers and see what you get. So it's the same model. Now I'm just going to train both layers. The idea here is basically I'm going to allow this layer to adapt its features to basically the data by combining, this guy over here. Okay, so long story short, I'm not going to go into the details of this, but so we get this is a full decomposition of all different scaling behaviors that you can get under the same assumptions. So this is the so-called lazy limit. This is what I showed you. I actually showed you just these two guys. And there's a bunch of other scaling behaviors you can get from finite size effect and SGD effects and so on and so forth. And this is what you would get in the feature learning regime. Okay, so some things match, some things don't match. Just to break this down, exactly what's happening over here.
Eta is learning.
There's an eta on this one. Oh yeah. I mean, it's okay, so there's a technical, so when you're calculating this, you have to scale these things in so this ratio is an ordered ratio. We can talk about that. Okay, so here is the long story short, the summary of it. So this is exactly what we can look at. All right, so it turns out, I mean, feature learning buys you a better exponent for certain tasks, but not other kinds of tasks. Okay, so it buys you a better exponent for so-called hard tasks, but not easy tasks. What are hard tasks? Hard tasks are those which are out of the RKHS of this kernel. Okay, RKHS is the recursive kernel limit space. So I mean, that's a fancy word, but what I mean by that is basically these teacher weights add up to infinity. So if these guys are adding up to infinity, then I'm going to get a better power law exponent from feature learning. If not, I'm going to get the same exponent. So this is basically showing you the loss exponent as a function of training time. We're going to do this. We're going to not think about the model not only while just for this second. All right. So so remember what beta is. So beta is how fast the eigenvalues of the task are falling. Right. If it's falling fast, that means it's an easy task. So here, basically, rich and lazy exponents match, and here, when the RKHS norms becomes infinite, you get a better exponent for formulas.
And the task, you mean the function itself?
The function itself, the function.
I guess that's kind of intuitive. It's just saying the NZK has some outward space associated with it, and this function is not.
Exactly, that's exactly what I was trying to say. Thank you. Exactly, out of RKHS, and therefore you have to do something, and then you gain exponents. Okay, so this is just verifying the same thing. This is a model. This is the linear network. So everything matches the theory. So, this is basically feature learning strength, meaning, so this guy is feature learning, that guy is lazy. And for easy task, the scaling exponents are the same. Now, there's an overall factor though. You still get like an overall factor gain, but the exponents are the same. And then for a hard task, you also get a better scaling exponent, overall factor. And this also shows these transitions from basically 1 over n to bottleneck scalings and so on and so forth. So you can get all these kinds of things as well. So this is exactly the setting of the theory, it matches. So we did this other experiment where we tried to apply this theory to review networks. So this is beyond what was done for theory. So what happens here? So we're going to define a set of just scalar functions. So y of theta is going to be a function of theta. They're just one dimension of theta. And then I'm going to expand this in terms of some Fourier series with power laws here, right? So k is the frequency here. And this is the q that I'm going to sort of, so the q here, so the beta here is a function of these q's over there. And then the corresponding kernel is over here. So by varying this q, I'll be having, hard or easy tasks. And basically what this is showing is like, again, the theory for review networks is actually able to, the predictions that I would make using the linear network seems to capture what happens in this case too, even feature learning case and lazy case. So this is success. Did we solve deep learning? No. Okay, so here's the failure mode. So for simple data sets like strands on MNIST, I do seem to get the both feature learning and lazy scaling laws by using this. But for harder tasks, like for example, C5M, I get the lazy one, that's easy. For the feature learning, I get up to a point, but then there seems to be a third regime, which doesn't be captured by this theory. I don't know what happens there, but that's what the state of the art is. Yeah. Yeah, go ahead.
For me, it was me. Good. Sorry, I wasn't sure. Just a question. So, just coming back to this question about the RKHS, there was this Google paper about the empirical finite versus infinite thing from 5 years ago. This large scale study across many different tests of whether the NTK was making good predictions. Have you revisited the different tasks in that paper in light of your RKHS?
I mean, that's a beautiful suggestion. I mean, that's to do with on our to-do list, exactly.
But your conjecture would be that the tasks that the NTK succeeds on are the ones that, the kernel is appropriate for the problem.
I mean, so the conjecture here will be like so in that setting, this was pre-MUP, so that's so we have to be careful about this. Yeah, so that's actually like a standard parameterization.
Yeah. Standard NTK.
Exactly. So it's a bit different setting. But I mean, so depending on how much you want to take this seriously, this particular prediction. So you may not believe the exact scaling, but you might buy the idea that there is a gain from feature learning when you're out of the Hilbert space of the initial kernel. So that particular thing can be tested, and it seems to be true for all the data sets out there that people do these kinds of experiments on. So if you look at if you try to diagonalize their kernels, if whatever sense you can, and you will find that the decay rate is actually going to hint that basically that is out of RKHS.
And the red dash line is your feature learning TMFT.
So the red dash line is the feature learning exponent that I calculated using the NTN. Yeah, so this is the feature. This is the lazy feature learning. These are different levels of features.
So red is already out of RKHS, and what the data is telling you is that there's, in this particular case, there's room to do better.
Yeah, so exactly. So the theory is saying, okay, see, this theory is exactly. So we're capturing this trend over here, but there's another acceleration. So that requires a bit more testing. Exactly.
Could you say again what lazy?
Lazy. Okay, so that's sorry. That means that's a jargon that people use by saying that networks do not adapt its internal representations to data. So the one way to think about a neural network is the following. This will be a very sketchy way of doing it, so it will be wrong, but I'll write it still. So maybe a network is a function of its inputs and its parameters, right? So you can expand this around its initialization plus data minus data 0. Then there's a grad theta f. And there are some projections. Okay? A lazy network or network in the NTK regime behaves as if it's a linear model of its parameters. Where you take data and pass it through some nonlinear features, and on top run a linear model defined by these parameters. So by lazy, I mean this particular model. And that's why I say in this setting, network doesn't learn its that network doesn't learn internal representations because this part depends on initialization. It doesn't adapt. I mean, there's a lot of papers which are trying to make this more precise, but that's what I mean. So, how much time do I have?
So 3:45.
Okay, so 15 minutes. Okay. All right. So let me try to give you again overestimate what I could do, but let's see. Underestimate. Okay. So let's talk about a different problem. At what scale capabilities emerge? So my goal here is now give you another solvable model for a different problem. And then we can cut this whenever time's up. So we're going to look at one of these emergent properties, so-called in-context learning. So this is a bit of a confusing term people use, but the idea is the following roughly. It's the ability to learn and execute tasks based only on examples seen in input without needing explicit training. So this is like basically you're writing on ChatGPT, you're describing the task, and then somehow or give examples of the task when you're writing, and it learns from those examples, but not its weights are not changing kind of. So here is an example. So you give sort of, this is what you write on the prompt, right? Input, output, input, output, input, output, inputs, and maybe you output, maybe you put a question mark or something, and the model has to produce this. Okay, so there is some kind of logic here, right? So I mean, you change the order of days and months and put like exclamation marks and so on and so forth. And the model has to learn this from basically what you give it to it. Its weights are not changing. This is the idea of in-context learning. Is this clear what this is? Okay, good. And then you know, this Brown paper, for example, argued that you know this appears at a certain scale. So what that means is we can start asking questions about like you know, to be able to, for this kind of a task to happen, how much should we train our model? How much examples should we give it? What kind of examples should we give it? Obviously, we're not allowed to give the same task, but we should be giving some different tasks. And context length, how many examples should we be giving one prompt? Can it learn from a single example or 5 examples or 10? What does it depend on? A lot of questions you can ask about this. All right, so here's another solvable model where we can address this exactly. And this is in-context learning for linear regression by linear attention. And there's, again, a lot of people who worked on this. And I'm highlighting a particular work from Ventus and Ganguly, which is going to be, they pose the empirical problem which we'll try to answer in this work. And my colleagues and collaborators, especially the US expertise in random matrix theory, was really helpful in this particular case. Okay, so let me try to formalize this a little bit. So it's a Bayesian model for ICL. So the goal is going to be this. I'm going to be given a bunch of XY pairs. I'll call this contexts up to L, and there will be a query token, XL plus 1, and the model is supposed to predict YL plus 1. Okay, and so one way to formalize this is following. So think of a collection of joint probability distributions on X cross 1. So for each input sequence, we're going to sample a distribution from this set. Okay, so we're going to sample a joint distribution. And we're going to generate a sequence of X's and Y's, IID from that distribution. And that's the idea. And the idea is, I mean, during so-called pre-training, okay, so when I'm training the model should learn the prior distribution. And so when I give it a bunch of context examples from that prior, then calculate posteriors and whatever it is that it's doing to be able to solve this task. So here's a simple way we can sort of try to pose a problem like this. And this is where the idea is the relation between X and Y is linear. Okay? So now I've changed my notation because now I'm collaborating with a mathematician. So now brackets are going to be dot products. Right? So X and W dot product is going to be given by Y. All right? So this is the idea is, you know, X and Y are given by, related by this task vector d-dimensional W. And then right, the model has to, just by looking at these examples and figure out what this W is and make a prediction. It has to solve some kind of a linear regression task. We can take some assumptions. For example, X might be coming from some Gaussian distribution. You can have some noise. So this is the important part. Now, every time I'm prompting this neural net, this model, I have to sample my W from a distribution. So it's a different W every time I'm giving it. So it has to solve this exactly in context. It cannot rely on past examples. Okay. So let's think about training such a model. So I haven't told you what the model is, but how would I train? Obviously, training, everything is linear. My word is linear. So in this case, I have to commit to a set of training Ws and generate examples of this sort. So the way I'll do this is basically committing to a set of K task vectors, meaning every training example will be chosen to be one of these K tasks. And then given this K, one of these K tasks, I'm going to keep adding, generating XY pairs. The reason I want to do this is because I want to have, you know, the idea of, you know, there's a training set of tasks, but the test set is different than those training sets. That's what I can get curious to. So for new sequence, sample the text vector W uniformly at random from W. Okay. Good. Cool. All right. So what is the model? So I have 2 slides. In 2 slides, I will be able to give my message in some math, but at least I can give you my main message. All right. So given the particular sequence, now this is, let's say, test time. I want to embed this to be able to fit to my model. The way I'll embed this in this particular way, I'll put x's on top vectors and y's at bottom, and every column is one example. And this is my prompt for complete. Okay. And then I'll pass this through a so-called linear attention module. So this is basically regular attention, but I remove the softmax. And the linearity has to do with computational scaling, but this is not linear in Z. I mean, this has 3 factors of Z that you're seeing. So it's pretty nonlinear model actually in terms of Z. And the V, K, and Q are the typical value key and coordinate matrices. The output of this is a matrix that has the same size as Z. So to be able to make my prediction, I'm going to look at this particular element, and that's what I'm going to read out. Okay. So, clear? Okay, cool. All right, so let's ask the following question. How can linear attention actually solve this task? Given it's what it can do, can it actually solve this task? All right, so what I'm going to do is basically just simplify my notation a little bit. So this is my value matrix. I'll call K transpose QM. And there's one parameter I set to 0. We can discuss why. There's a good reason to. And under that constraint, it turns out the network's prediction can be given by this form. So it's a trace of a matrix that only is a function of these parameters. And H is a random vector, a vector here, which is basically a matrix in this case, actually. Here, that is a function of what I provide at the prompt. Okay, so these are the parameters. This is what I provide. So if I look at what's happening here, I can sort of see how this neural network can solve this problem. So you see, here's what it's doing. So let's look at this term over here. It's multiplying x's and y's. This is sort of like calculating a correlation, right? So remember, y was w dot x. So this is w times xx transpose, right? So if you have enough many samples within one context, this will be a good estimation of the data x covariance multiplied by w. So if you were somehow able to invert that covariance by matrix by learning the parameters, this is going to basically give you w dot x, and you're going to solve the problem. Right? So in context, this is actually doing some kind of data estimation, so covariance estimation. So just from here, I can actually just intuitively answer a lot of questions. So for example, we talked about how large should the context length be. Well, I mean, this should be a reliable covariance estimate. So suppose I'm dealing with high-dimensional vectors, x is d goes infinity, and this context length should at least linearly go to infinity, right? Otherwise, I won't be able to do this covariance estimate. So that answers that question. How many training samples should I have? The effective number of parameters basically is d squared. You can see it here. So basically, and this boils down to a linear estimation, a linear regression-like problem. So number of training samples should go like d squared. And then, and there's another, okay, task complexity. So how many training tasks should I have? That turns out to be a hard problem, but it will go like the as well. Okay. So the rest of the work is basically turning what I just told you in a solvable problem. We train this on a square loss on this model, okay? And you know, this is a linear regression problem, so we know the exact solution, which is a horrible looking random vector, which all kinds of tensorized stuff. But then we got stuck there for a while, and then we find our colleague Yue, and he knows exactly the trick, and he helps us solve this. And then move on from there, and then calculate exact generalization errors. And then, but we're going to test this model on 2 kinds of errors, test distributions. One, I'm going to give basically examples, W task vectors that it hasn't seen in training set. So I'll call this in-context learning test. And the other one is going to be in-distribution generalization. I'll test it exactly on the examples that it has seen. Okay, so long story short, we can define a joint asymptotic limit where number of dimensions and context length go linearly together to infinity. And number of context sequences in the pre-training set goes again to quadratically with input token dimension, and the task diversity goes linearly with complex dimension. So in token dimension, and this turns out to be the right limit to get some phenomenologically interesting behavior. And then basically write down solve this random matrix theory problem and come up with joint asymptotic behavior of these tasks. So I'll show you one phenomenology that's interesting, and then I'll finish there. And we're going to compare our behavior to two Bayesian estimators. Okay, so now separate guy. So one guy will be the ridge estimator. So this is just going to look at the examples that have been prompts and do a ridge regression. And the other one is going to basically look at those guys, but do, as a prior, assume that the task vector is one of the training guys. Right? So this will be like sort of I memorize what's in the training set. This is I'm totally doing context learning. And then, so here is what Raventos et al. Found. This is an empirical study from before. So this is number of training tasks in the training set. So there's two curves here. Okay, this is the test error, and this is basically so this is the behavior of the DMMSE estimator. This is assuming that the task is one of the K things I've seen, and this is assuming that basically the ridge estimator. Okay, the model early in number of pre-training tasks behaves as if it's like a DMMSE estimator. It has memorized what's happening in the training set, and here it becomes basically a ridge estimator. And basically, we can recapitulate this behavior in our model and relate that to a particular phase transition that happens as basically certain quantities goes to infinity. We can sharply show that this model actually does collapse to ridge estimator above number of tasks becoming more than number of dimensions. So this is a very sharp transition and emergence happening here. Below that, you don't have this behavior. Above that, you have this behavior. So I took a lot of your time. I'll finish, and this is basically showing that not the exact predictions, but the scaling behaviors we've identified holds for more realistic neural networks as well. And then I want to thank my students and collaborators on this one, and thank you very much.